Hello students, welcome to part 2 of our topic on real numbers. In this session, we'll explore irrational numbers, proofs, rationalization, surds, and properties of real numbers. Let's continue. Irrational numbers are those that cannot be expressed as p divided by q, where p and q are integers and q is not equal to 0. Their decimal expansions are non-terminating and non-repeating. Examples include square root of 2, square root of 3, pi, and e. Let's prove that the square root of 3 is irrational. Assume square root of 3 equals p by q, where p and q have no common factors. Squaring both sides, we get p squared equals 3q squared. That means p squared is divisible by 3, so p is divisible by 3. Let p equal 3k. Substituting, we get 9k squared equals 3q squared, or q squared equals 3k squared. So q is also divisible by 3. That means both p and q have 3 as a common factor, which is a contradiction. Hence, square root of 3 is irrational. Now, is square root of 2 plus square root of 3 irrational? Yes, because they are not conjugate pairs. In general, the sum of two irrationals is irrational, except when they are special pairs like square root of 2 and minus square root of 2.
Sir, can the sum of two irrationals ever be rational?
Yes, it can. For example, square root of 2 and minus square root of 2 gives 0, which is rational. Rationalization means removing the square root or surd from the denominator of a fraction. We multiply the numerator and denominator by the conjugate. Example, 1 divided by open bracket square root of 3 plus 1 close bracket multiplied by open bracket square root of 3 minus 1 close bracket divided by open bracket square root of 3 minus 1 close bracket. Simplify. Numerator is square root of 3 minus 1. Denominator is 3 minus 1 equals 2. So, the rationalized form is open bracket square root of 3 minus 1 close bracket divided by 2. Let's recall some important properties. Square root of a multiplied by square root of b equals square root of ab. Square root of a divided by square root of b equals square root of a divided by b. And square root of a squared equals absolute value of a. Example, square root of 2 multiplied by square root of 8 equals square root of 16 equals 4. Real numbers follow three main properties. 1. Commutative, a plus b equals b plus a, and a into b equals b into a. 2. Associative, a plus within brackets b plus c equals within brackets a plus b close brackets plus c. 3. Distributive, a into within brackets b plus c equals a b plus ac. Example, 2 into within brackets 3 plus 4 equals 6 plus 8 equals 14. Terminating decimals are rational. Non-terminating repeating decimals are also rational. Non-terminating non-repeating decimals are irrational. Example, 0.6 recurring equals 6 by 9 equals 2 by 3, which is rational. Suppose x equals 0.2727 repeating. Multiply both sides by 100, we get 100x equals 27.27 repeating. Subtract x from 100x, giving 99x equals 27. Therefore, x equals 27 divided by 99, which simplifies to 3 by 11. Let's check if 7 divided by 40 is terminating. Denominator 40 equals to raised to the power 3 into 5 raised to the power 1. Only 2's and 5's are prime factors, so 7 by 40 is terminating.
Sir, how do we find the number of decimal places?
Express the denominator as to raised to the power m into 5 raised to the power n. Then convert it into 10 raised to the power k, where k is the maximum of m and n. That k tells you the number of decimal places. Let's do a quick check. Find HCF of 20 and 28. 20 equals to squared into 5. 28 equals to squared into 7. So HCF equals 4 and LCM equals 140. Remember, Euclid's lemma supports the fundamental theorem of arithmetic, and that theorem supports finding HCF and LCM. All these ideas are linked beautifully in number theory. Let's summarize what we learned in both parts. 1. Real numbers equal rational plus irrational. 2. Euclid's lemma helps find HCF. 3. Fundamental theorem of arithmetic gives unique prime factorization. 4. HCF multiplied by LCM equals product of the two numbers. 5. Terminating decimals have denominators with only 2's and 5's. 6. Irrational numbers are proved by contradiction. 7. Rationalization removes surds. 8. Real numbers follow commutative, associative, and distributive properties. That's all for today. Keep practicing these basic number ideas. They form the foundation for algebra, polynomials, and beyond. See you in the next class. Jai Hind.